Great. Good morning, everybody. We're going to get started. So I'm Blakesley Burkhart. I've been the one spamming you for the last couple weeks. I'm glad everyone made it here despite the somewhat nasty New York weather, but we're all here now and we're going to get started. So Mike, Shelley, and I wanted to orient you a little bit where you are, what this place is doing. I know many of you are here for the first time. So welcome. We're also going to go over just a couple logistical aspects of this meeting. We're a very diverse group, and so we just had a few points we wanted to make for all of us to keep in mind so that the meeting is going smoothly and we're all learning something.
Hi, I'm Mike Shelley. For those of you who don't know me, that's Blakesley's.
It's actually Melanie's, one of the organizers. Yeah.
Extraordinary. Okay, so let me just say a little bit about where you are. So you are in the building of the Flatiron Institute. We're directly across the street from the mothership, which is the Simons Foundation. And we started in 2016 with, I think, the two original centers were the Center for Computational Astrophysics and the Center for Computational Biology. And we represent those two entities. We also have here a Center for Computational Quantum Mechanics, Quantum Physics. Oh, it says materials here, and Center for Computational Mathematics, which is, as I like to say, kind of the glue that binds us all together, kind of computational methods, really. And that number is somewhat fungible, but as it says here, we're funded for the long term. So we're going to be here for a while. We have a new center that's going to be starting in the coming year in computational neuroscience, and that should, at least for the moment, round out the computational science centers that we have going on here. Oh, wrong way. So a little bit of background. This is CCA, CCB, and the Flatiron Institute, where what's the overall mission? Advanced scientific research through computational methods, including data analysis, modeling, and simulation. I think that says it all. That covers what goes on in all of the current centers. And I'll let Blakesley take over here.
So yeah, this meeting is being jointly hosted by the Center for Computational Astrophysics and the Center for Computational Biology. So we were really excited about this idea that turbulence is one of these topics that bridges multiple communities. We have multiple communities here in the Flatiron Institute. So I'll just say a few words about CCA. So CCA obviously is broadly focused on computational, numerical, and statistical methods as applies to astrophysics. We have several different groups, basically, that make up CCA, including galaxy formation, data science, compact objects, gravitational waves, cosmology, planet formation, and now the newest group is a group that focuses on dynamics. And we have a small core of people here who are here in the long term. So they're research scientists, group leaders. We also have some people who are cross appointments. So I'm an example of one of those people. I have a joint appointment here, and I'm also a professor at Rutgers University. We also have a sabbatical program. So if you are excited about this place and you want to spend your sabbatical here, please apply, especially if it's CCA focused. We have the sabbatical program that's now become very successful in the last few years. Of course, we have a large cohort of postdocs and fellows here. And then we also host short-term visitors. So there's a lot of opportunity for you to come back to collaborate with all of us here.
Okay, so now it seems evident that if you're talking about turbulence modeling, you involve a lot more CCA than perhaps you do of CCB. As some of you know, I come from a fluid mechanics background. I have lots of pals that do turbulence, so that was kind of my side in helping organize this. But just a little bit about CCB, most of which is not directly relevant, so to speak, to this meeting. So we cover certain areas of computational biology, which is a kind of a very large subject. So I run a biophysical modeling group, and we do some work in active materials and active fluids and things like that. And there will be some talks here in those areas. We have a new group that just started with Stas Schwartzman in developmental dynamics. We have a genomics group with Olga Troyanskaya does more analyzing the sequence and looking at disease relations and things like that. A neuroscience group headed by Mitya Klosky, and a systems biology group with Rich Bonneau that does a lot of structural biology problems. So we are very group oriented. So each group is a group leader and then a mixture of permanent, long-term, and then postdoctoral research fellows. And so like CCA, we have a number of shared appointments amongst our group leaders in particular, which is a little bit different, with NYU, Princeton, and the NYU Medical School. And we have a mix of other types of scientists. We have various types of titles that we've given things that handle things in computational biology. And we also have visiting scholars. And again, this is if you want to work in kind of biophysical modeling and soft matter research and things like that, I'm probably the place to go if you want to spend some time here. Or CCA, though you're not so much soft. Okay, so let's see. Oops, I backed up. Rules of the road. We're live streaming. So you may notice that you have a little button right here. Everything's being recorded, and so if you press that button, we ask that you press that button when you ask a question, then it will be recorded for posterity that you asked that question.
Also for the benefit of the people who are listening in on Zoom,
oh yes,
that they can hear your question.
Yeah, good. It's a broad group. Do not use jargon. Blakesley, you want to address this last?
Yeah, I mean, so we're coming from different perspectives, right? From math, from plasma physics, from astrophysics, from biology, from atmospheric science. So obviously we all have our own lingo, and we perhaps don't even agree on what we mean by turbulence, right? So it's going to be an exciting meeting, and just that everyone keeps in mind that the audience is very broad. And I know I'm giving one of the first talks. I'm sure I'm going to slip up a few times. I changed parsec to light year, et cetera. So, just... Ethan's an editor, so this is an editorial question I'll leave to you. Just to keep that in mind, right, that we are a broad group.
And no food or drink in the room. They get pretty strict about it. So we'll turn it over to James.
One last point for this final point here. So we're going to have some discussion sections throughout the days, but our main interactive discussion day is going to be on Friday, and we're collecting some topics for breakout groups. So if you have an idea or if you'd like to lead a breakout group, just please come see me, and I'll add it onto this Google Doc that we're collecting these ideas for Friday's unconference session. Okay, and that's all we had in terms of logistics, and we'll turn it over to William.
Okay. So, well, first of all, thank you very much to the organizers for putting together this very interesting program. I'm always tickled when there's an interaction between different communities and a sort of broad exchange of ideas. So I'm very excited to see the talks that come. I've tried to make my slides as clear as possible and avoid as much jargon as possible. But maybe this is a good moment to say, please feel free to interrupt and ask questions if you don't understand anything. I'd much rather have a good discussion and a dialogue than get through everything. So I'm going to focus on experiment. And in particular, I'm going to focus on the experiments represented by the two images that you see over here. On the left, you're looking at a photograph. It's a photograph taken in our lab. And the scale of the structure is about this big. And what you're looking at is light scattered off air bubbles in water. And what's interesting about this image is, of course, not the light bubbles, the air bubbles themselves, but what they're showing you about the flow in this tank. And in particular, what they're showing you is that in this tank, there is a vortex loop, something like a tornado or a vortex ring, that has been twisted around and tied into a knot. On the right, by contrast, is a computer-generated image, but it's a computer-generated image derived from data. And what this is showing you is the kinetic energy inside a tank, which is roughly the size of this octagon over here. And so what this image is showing you is that inside this tank, The scale of this blob in real life is about 10 centimeters. And what this is showing you is that inside this tank, there's this concentrated region of kind of, we'll call it turbulent for the moment, but sort of lively fluid flow surrounded by the quiescent flow around it. So the sort of common thread is really experimentally designing vorticity in the lab, both in its sort of coherent forms and less coherent forms, with a view to studying fundamental problems in fluids, for example, conservation laws, in particular conservation of helicity, or with a view to generating kind of turbulent model systems or model systems in which one can study maybe the effect of things like helicity on turbulence, but also just kind of sort of try to play with inhomogeneous turbulence and spatial inhomogeneous distributions and systems where you could inject various quantities and sort of have fun. So what underpins everything is vorticity. And of course, vorticity does not underpin just what I'm going to tell you about. It underpins, if you like, all liveliness in fluid flow. So as probably everybody in this audience knows, in a fluid, say an incompressible fluid like water, in the absence of vorticity, you have no life. You have no liveliness away from boundaries. The flow has to be potential. And so in order to have structure away from a boundary, and in order to have dynamics, you have to have vorticity there. And the quintessential vortical excitation that sort of embodies this is a vortex loop, right? Such as the one that you see over here. Right? So I think everybody's familiar with this. If you're not, what you're looking at is a flow in which there's no vorticity sort of almost anywhere except concentrated inside this ring. So this is a flow where there's literally no vorticity except for a bundle of vorticity concentrated inside this line over here. And they're very easy to make. As you saw, in this case, we just puffed a little bit of fluid out of this orifice. And the reason you can see it so easily is that we've seeded the fluid with air bubbles. And so if the vorticity is concentrated inside this loop, the fluid is spinning around this loop. And so the air bubbles are attracted to the center of the spinning simply by buoyancy or by inertia. And so that enables you to see where the vorticity is. And these are very nice structures experimentally. They're very synthetic structures. So for example, from this, I can reconstruct the entire flow field in the tank. All the information that I need is contained inside this ring. And in fact, not only can I reconstruct the flow field, but I can also kind of infer its dynamics. So as a reminder to almost everyone, but perhaps not to everyone, this is the law of motion for vorticity. And it has in fact, at these sort of scales, at high Reynolds numbers, in phenomena which don't really involve viscosity, it has a very nice interpretation, which is simply vorticity goes with the flow. Right? So the way that you can sort of think of the evolution of this structure, which is sort of maybe, is clearly evolving away from a boundary and bringing life to the fluid far away from the boundary, is that it's basically moving itself. So you think of this vortex loop as generating a flow field and then just being advected by that flow field. Now, this is perhaps sort of boring dynamics. It doesn't take much to get a lot more dynamics in a vortical flow. Here's an example in which we shot two vortex loops, one after the other. And you can see this law of vortex motion in action. They're advecting each other and kind of dancing around each other, eventually merging at a later stage. You can also just take a simple vortex loop, and instead of having a ring, give it a little bit of shape. So for example, here we just made a threefold distorted shape, and you can see this evolves with a kind of lively dynamic. It almost looks like an elastic filament that is oscillating, but in fact what you're seeing over here is another example of the simple law of vortex motion. Right? If you had a straight vortex, the flow would just go around it. It wouldn't advect it. It wouldn't move. If you curve it, neighboring points can now contribute at the point in between them and push it along. So you get a velocity that depends on curvature, and that's what you see in action over here. You see the vortex loop sort of, the curved regions going faster and the anti-curved regions going backwards. And you see the structure flapping. Okay. So this notion of sort of advection, dynamics by advection, underpins all these motions. But it also underpins some additional things. Oh, yes, sorry. So one thing I just wanted to point out at this stage is this notion of advection, of a structure generating a flow, and then in turn that flow advecting the structure is common, I think, to all our fields. It's certainly common in vortex dynamics. It's also common in some of the active matter which we're going to talk, in which topological defects in nematics generate flows and then advect and give liveliness to the flow. And I think to some extent it's also true in plasma physics, but please don't quote me on that. Okay. And this idea of advection underpins not only sort of gives us an ability to look at these dynamics, but it also underpins an exciting kind of idea, which is not a new idea, which is that in fluids, lurking in our sort of equations of Navier-Stokes equations for energy, momentum, and mass, there can be an additional conserved quantity. And this conserved quantity was discovered in the late 60s by Moreau and by Keith Moffat, and is known as the hydrodynamic helicity. And it has some analogs, I think, in plasma physics, for example, in the magnetic helicity. And it's given by this expression over here. It's just the dot product of the velocity and the vorticity integrated over all space. And it was discovered, if you like, the old-fashioned way. Right? It was discovered by constructing this quantity, putting it in the equation of motion, and seeing that it is an invariant quantity under the equation of motion. So it didn't come from a symmetry, the usual way we do things post-Noether theorem in physics. And so it needed an interpretation. And thankfully, Keith provided this too. I'm writing an equation over here in sort of cartoons, but it's really a statement about differential geometry. What Keith showed is that this quantity over here, the helicity, can be understood by simply taking your vortical flow, your flow field, computing the vorticity, dividing the vorticity up into vortex tubes or vortex lines, and then calculating what is in fact the Gauss linking number between all the pairs of vortex line, which is a topological invariant that characterizes these lines. And if you sort of weigh it by the circulation and add it all up, you get the helicity. Right? And now you can sort of see, perhaps intuitively, where this conserved quantity comes from. In an inviscid fluid, right, the dynamics that I've described so far apply. And so if you make things with topology, vortex lines cannot cross because they're simply advecting each other. And so things that characterize the topology of vortex tubes must stay invariant. Now, that is true, of course, in inviscid fluids, but and you can make similar statements about the idealized versions of plasmas, of viscous fluids, so dry water and quantum fluids. But as many of us know, in real fluids, where you have dissipation, in fact, even a small amount of dissipation, you sort of have the singular behavior is enabled. And this singular behavior enables the cutting and splicing of vortex lines or magnetic field lines or things like that. Right? And so this sort of notion of this inviscid advective behavior, which protected the helicity, is sort of broken. And it looks as if this conservation law is under serious threat. Now, the question then becomes, of course, one could walk away and say, okay, this is useless. Or one could ask, what is the balance of helicity in real flows? Right? And for example, kinetic energy is not a conserved quantity, the action of viscosity, but it's still pretty useful. So you could ask, what does helicity do over here? So we decided to try and go after this question, and we thought that it's a fundamental question. It's a basic question. We should try and do an experiment to get at it. And part of the reason is that we wanted to do an experiment is that these problems of reconnections are very singular, so they're hard to treat analytically. And at the same time, there's large separations of scales involved in these problems, which makes them challenging computation. So we decided to set out and try to build some topology in the vorticity in the lab. And in fact, in the interest of sort of being able to get to some recent developments, I'm going to make a very long story short. We tried all sorts of approaches. I could show you videos all afternoon. We tried shooting vortex loops together. We tried making holes where the edge of the hole is tied into knots. And we spent a long, long time. In fact, we discovered after trying these things that several people had tried before us and everybody had sort of failed. So I'm just going to fast forward to the solution that we found. And the solution is actually a familiar object. It's what brought many of us together today. It's a wing. And as everybody knows, a wing in the steady state has a circulation around it. And this circulation develops in the process of acceleration of the wing by the emission of a vortex of the opposite sign, which gets left behind. Okay, this is known as a starting vortex, and it's a well-known phenomenon in aerodynamics. So what we decided to do was to take this and make it into a sort of experimental tool for designing vorticity. And so we took the profile of a wing, and then we decided to make wings which were closed, and in particular wings which were closed loops and perhaps tied into knots as methods for trying to generate vortex knots. You can make these easily with 3D printing. It takes a little bit of finesse and a pretty good 3D printer to get it to work, but it's once you have it, it's pretty straightforward. We mount these in a tank. We put a little bit of bubbles. In this case, they're just spontaneously formed on the surface. And then we accelerate this impulsively in order to leave behind the starting vortex. And what you can see is that it sort of it works. Right? It sort of looks promising. This is a two-dimensional movie. Everything I'm talking about is really in 3 dimensions. So let me show you what happens in 3 dimensions by taking a laser sheet and scanning it across our fluid and synchronizing this with a high-speed camera. We can record at about 500 volumes per second, and then you can sort of watch this vortex being created and evolving in 3D. Okay.
Sorry, I have a question.
Yes.
What's the typical lifetime of the nuts?
Excellent question. So give me 2 slides, and I'm going to answer that question. That's a very good question. Okay. So incidentally, you don't just have to make knots. You can make anything you want, any shape of vortex that you want, and we're very happy to share this technique. So if you're interested, please contact us. We're happy to either send you the hydrofoils or the design for them. We're very happy to have this technique be adopted in other labs. But everything I've told you so far is really just a technique, and the question, of course, is, let me skip this. The question is, of course, unless you have questions about it at the end, the question, of course, is what happens, right? And how long does this knot live? There's all this song and dance about conservation. If this thing falls apart, what should we think? So let me jump right to that. Here's that movie, but where I continue to play it through for a longer time. There have been all sorts of predictions about what the dynamics should be. Maybe these structures should preserve their shape and evolve, without distorting. They should simply rotate and translate. There's all sorts of other predictions. But what we saw was this. Right? So basically, the structure stretches, which is not obvious from this, and disconnects into separate linked rings, unlinked rings. And this proceeds through a sort of coordinated set of reconnections, like what I mentioned at the beginning, in which anti-parallel strands approach each other and disconnect. Okay. So this is all coming, of course, from the part of the equation of motion that we ignored before, the viscous part, right, which is now able to have a big effect because we have strong gradients in vorticity. And so, the question is, what happens now, right? Have we lost all of our helicity? We've made a knot. The knot has fallen apart. What's happened to the helicity? Right? So one could take a pessimistic approach and say, well, we've lost it, that's that. But in fact, if you think about it a little bit more, you realize that this viscous term, which enables these reconnections, actually also does something else to vortex loops. It endows them with a thickness. Right? You have a diffusive term for vorticity, so you can't have a line, you have to have a tube. And if you have to have a tube, then you have a distributed vorticity inside this tube. As soon as you have a tube, you should think of these objects not as a single line, but as a bundle of filaments. And if you have a bundle of filaments, you can imagine weaving them together to store helicity. Now, this is kind of it's a long mathematical topic, a very beautiful one. There's some seminal contributions. I particularly like this paper by Berger and Field from the sort of plasma community. The nice thing is that all the complications boil down to geometry, and so you can express the outcome in very simple terms. Helicity for something like this has basically 3 geometrically distinct contributions. The first one comes from considering 2 tubes, each one with a trivial structure inside, where the vorticity is simply parallel transported along the center line of the tube. And that's sort of what we've been having at the back of our mind this whole time. You can compute the helicity of something like this by computing this linking number, which is 1 in this case. You subdivide this tube into n filaments, and you look at each one is linked to each one of these, and there are n to start with, and there's n to which it's linked. And so the helicity of this is 2 times the circulation squared. Another way of storing helicity, however, comes from taking a simple tube, a ring like the one that we've been seeing, putting a twist inside it by 2 pi, and closing it. And you see the geometric effect that this has had is to take this sort of structure and link every subtube to every other subtube. And if you do the accounting on this, you find that, in fact, it's very efficient. We only get a factor of 2 compared to the 2 linked tubes. So internal structure is efficient at storing helicity. And this one is a sort of local internal structure coming from the vortex lines twisting around each other. You can tell that there's twist locally. The third contribution comes from taking that and trying to make it as much as possible like the parallel one that we saw over here. Right? So you're kind of just distorting it. You're not changing the value of helicity, but doing that, making everything locally parallel, requires you to introduce coiling in the vortex. That's a little bit like a Berry phase, and that's, if you like, our third mode of storing helicity inside the tube. So we have these three. If we looked at this one, we thought we lost everything when the knot fell apart. So let's include at least these two and see what happens again. So here's a slightly different experiment. These are two linked rings which are falling apart. This is the linking, which goes from this is a sort of helicity related to linking, which goes from 2 to 0 at the moment of reconnection. If we include the coiling, what we see is that we start with sort of 0 contribution, and this stays 0 up until the moment of reconnection. Okay? But then what we found is that right after the reconnection, this contribution jumps, and it jumps roughly by what you need in order to have the sum of these two be conserved. And so this is kind of was a sort of struck us at first, and we investigated it quite a bit. And what we found is actually it's quite a general mechanism. You can see it in this cartoon I'm showing you over here. You have the structure, it distorts, but when it reconnects, it introduces all this coiling in the structure. And once you've seen this, in fact, once you've done a lot of experiments, which I'm not showing you, of all sorts of knot types and shapes, you realize that this is actually quite generic behavior, sort of universal behavior. And in fact, you can make it into a theorem. And the theorem says that if your reconnection is locally antiparallel, then the helicity will be exactly conserved through a reconnection. It's a sort of surgery theorem that you can deduce from this. Here's an example of that evolution of the sum of those two contributions for this case over here. So the thing that we thought would kill the helicity actually doesn't have to kill it at all. So we thought this was sort of interesting. So we thought we should dig deeper. And in particular, we thought we should start to try and address the twist. We should look inside the vortex tube. So we developed some new technology to do this. We sort of placed inhomogeneous dye on the trailing edge of our wing. This diffuses with a good time scale, which then enables us to place it exactly in the core of the vortex. With some simple assumptions about the structure of the vortex, we can then compute the helicity by measuring the flows along the vortex core as long as it's reasonably laminar. So here's an example of an experiment in which we took then a helix and we stretched it out with this leapfrogging action using a bigger ring. And now what we're able to do is not just simply follow the evolution of the line itself, but follow the flows along the line. And so I'm showing you here the trajectories taken by all the blobs of dye along this thing. So then we can take this and we can go back and we can compute the total helicity, not just the linking and the coiling contributions, which I've talked about so far. And so here's the coiling contribution, right? We've taken this helix and we've stretched it out, so this goes down. But if we compute the total helicity, we see that stays relatively constant. And so what this is showing you is that even though we're inside the viscous core of the vortex, you still have room for inviscid behavior, like the one that you see over here, in which the vortex core is sort of stretched out, and that converts this coiling into this twisting inside. So that was a kind of stretching experiment, and then we decided to do one where we just make a helix and let it evolve, and just watch what happens. And so this is a sort of trajectory movie, and from this, you can go and measure again these different contributions. And the coiling sort of stays, well, not quite constant, but it increases sort of gradually. It doesn't have any dramatic dynamics. But when you sort of plot the total helicity on top of that, you see something very different from what we've seen so far. Right? And we sort of expected this at some level. Viscosity has to play a role in this story. And what you see is that the helicity, in fact, increases, changes in value, increases from almost 0, but it increases to a value that sort of plateaus, not to some random value, but it plateaus to meet exactly the coiling contribution. Okay? And this is sort of generic again. If your coiling isn't varying strongly, that is what the helicity will do. Okay? And we thought this was sort of interesting, and we stared at it for a while. It confused us, but then we realized that actually it has a very simple and natural take-home message and interpretation, which is if we think about the three contributions to helicity, we had linking between tubes. This is clearly non-local. Right? Then we had coiling, which is like a Berry phase. This is also clearly non-local. And then we had twisting, and this was the only local one. And so for viscosity, which is sort of acts locally, should act on that contribution, the twisting one. And the dynamics that you're seeing over here can be understood as taking a twisted tube and making it all locally parallel transported. Okay? And the outcome then is that the helicity of this tube will be exactly given by the coiling of the tube, so the non-local contribution. So even when viscosity is acting, if you have these sort of intermediate situations where you have some coherence in the evolution of the vortex, the geometry of the vortex is still governing the value of helicity, even though it's viscosity that's acting very, very strongly. Okay. So we're sort of pursuing this line where we're playing with we're sort of now trying to use helicity to engineer unstable dynamics in vortices and try to get to the bottom of some of the statements that I've made, which these experiments sort of showed, but we really want to work out quantitatively. But I don't want to continue talking about this. I want to make a connection to the second part of this talk, which is turbulence. So let me just summarize that first part. What we found is that if you make kind of coherently engineered vortices with topology in the lab, they all fall apart. Right? And in fact, this is a sort of actually universal thing. We've tried every knot in the knot table under 10 crossings. You can try even more complicated things. They all do the same thing. They all stretch and they all disconnect. They all want to expand. Right? That's an idea to maybe keep. But in the process of doing so, during their reconnections, they don't actually lose any helicity, right? Because we have this kind of anti-parallel-like reconnections, which enable it to be conserved. And in the process of being stretched and folded, they also don't seem to lose helicity. The way in which they lose helicity, or in which the helicity value changes, comes from the viscous dissipation of the local contribution of helicity, which is twist. So you know, how important or how useful helicity is to interpret all sorts of vortex dynamics is still something which we're pursuing. But one of the natural questions which at least we wanted to ask at this point is, well, okay, so if helicity does anything interesting, it would be really cool if it did something to turbulence. Okay, so we started thinking about the idea of using the technology we developed to make vortex loops with controlled helicity and use that to inject that into turbulence in a controlled way to try and see whether or not helicity has an effect on turbulence in the hydrodynamic case. I think there's a lot of interest in this in MHD, but we're focusing on hydrodynamics. And so we started playing with the idea of combining a lot of these vortices with non-trivial helicity and putting them together to try and make a turbulent blob. Okay, and see if helicity has an effect on turbulence. Now, I should make a spoiler alert right here. I'm afraid I'm going to disappoint you in the sense that I'm not going to have an answer to whether helicity has an effect on turbulence. But what I want to show you is the progress we've been making towards being able to address this question. And also, hopefully, in the meantime, you'll also see that we're developing a system which I think is an interesting one. And so all this is kind of very much work in progress. We're doing this at the moment. It's all unpublished. And I'd be particularly grateful for feedback and discussion on some of these secondary aspects. So if you like, the perspective I'm taking now is we think of this as a soup of loops, as a soup of vorticity. And what we want to do is we want to build this soup by throwing together loops one at a time. So we sort of want to construct a distribution of turbulence by combining lots of loops together. And so the first question which arises is, well, if you shoot lots of vortices together, if you sort of try to construct a state like this in this way, does it work? Right? If you fire lots of vortex loops together, do you get turbulence? Or what happens? And so we tried, and we tried with, the simplest thing first. We tried taking two vortex loops. Actually, we tried this, but what I'm going to show you here is not what we tried. It's just an iconic movie from the 80s, an experiment done in Japan, in which they took two vortex loops and fired them at each other. And if we try this, we get something vaguely similar. And this is beautiful. This is amazing. There's a lot of physics and vortex dynamics in this movie. The feature which I want to highlight is we shot the vortex loops together, and all the vorticity ran away and escaped. It didn't stay there, and it didn't make turbulence, at least not anywhere near it. So let's try something very naive, much less beautiful video. Let's try with 4. And we thought, let's see what happens. So we have a box. We have 4 holes in the side of the box. We pull fluid out of this box. and this generates 4 vortices that collide. Okay? And it's not immediately obvious from this movie what's going on, so let me replay it, but let me show you next to it a sort of cartoon, guide to the eye what's happening. And what you see is that what's happening is actually quite the same, not as beautifully visualized, but it's actually the same as what was happening before. The vortex loops come together, they reconnect, and then they fly apart. Okay? In this case, out of plane. Okay, so in a sort of streak of unoriginality, we thought we would try 8 holes. So these are the corners of a cube. Let's see what happens here. There's a point to this eventually. And actually what we found was the same thing. Okay, so again, that's not super easy to see, so let me show you a cartoon that illustrates it. We fire the 8 rings together, they reconnect and they come out. Okay? So we started doing statistics on this, repeating this experiment, repeat it, in this case, once per second. You can measure the sort of energy distribution with PIV and the entropy distribution. And what you can see is that nothing is getting in the middle, right? Everything is coming in and going out. But we're sort of playing with this, and we were sort of playing with the parameters. And one of the parameters we varied was the frequency. We were trying to get statistics, so we were just repeating the experiment. We repeated it a little bit too often. And what we found is that actually something interesting can happen if the outgoing rings have a chance of interacting with the ingoing rings. So you can see over here that after a couple of shots, this is sort of not super clear footage, but after a couple of shots, you can start to see that the incoming rings are being distorted by the outgoing ones, and there's sort of a lot of interaction, and something different is happening over here. So we immediately sort of measured, used PIV to try and measure the velocity distribution here and the entropy distribution. This is sort of the cartoon that we had in mind. We said, well, maybe if we fire a lot of them, something will get to the middle. And this is what we saw, right? And so what we saw is that basically just by increasing the frequency a little bit from 1 to 5 hertz, and allowing these vortex rings to interact, the ingoing with the outgoing, we had a big change, right? In particular, we saw that the vorticity penetrates all the way to the center, and in fact is peaked in the center. So firing these sort of in this kind of tickling way, if you like, brings about a big change, right? We go from a shell in which no vorticity penetrates to a state in which the penetration occurs and all the vorticity is sort of inside this blob. So we thought this was sort of exciting. This is sort of, if you like, our hope at the moment. We have to address it. We have this localized state, right, in which the vorticity is all confined inside some region. Is it turbulent? Well, we have to think a little bit more carefully about that and be very careful with what we mean by that. But certainly we thought we should look at it more carefully. And so the first thing we did, we asked is, well, maybe some of this is escaping, but it's escaping in a plane which we're not seeing. Right? So we thought we should look at this structure in 3D. And so we took our laser scanning sheet and we upgraded it to do PIV. And then we composed all these PIV images together to get a rough picture of the energy distribution, the average energy distribution in this experiment. And what you can see over here is sort of the feeder tubes. So you can see the vortex rings coming in. But what you can also see is that otherwise there is no escaped vorticity. Everything seems to condense more or less in this region over here. You can take a cross-section through it and kind of look at the extent to which the energy is homogeneous and how it's distributed. And one of the things that you can see is that it's actually quite a sharp interface, right? It's sort of fairly tightly confined. So it's sort of fairly homogeneous on the inside. This sharp interface is sort of, maybe that's coming from the color or not. So let me show you a quantitative measure of this sharpness. If we take the energy distribution and we average it, right, inside the blob, if we average it sort of azimuthally, then we get something that looks like this. Right? So it's reasonably homogeneous inside. This is a log scale, so there's a little bit of variation, but reasonably homogeneous on the inside. And then at some scale, which will vary in these experiments, in this case around 10 centimeters, a little under 10 centimeters, the energy distribution, kinetic energy distribution starts to drop quite sharply. So we have a sort of sharp interface. Yep.
What happens if you turn off all the vortices coming in?
5 slides, if we get there, if not in question time. It's an excellent question. Okay. So we have this sharp blob. Our vorticity is not escaping, so we've condensed all this vorticity into a region. what's going on inside this region. Is this, is this turbulent in some sense? Is it not? Let's have a look. And so one thing, the simplest thing which we thought we could do to try and look inside and get a handle on this question was to maybe look with a little bit more detail. So we're doing particle imaging velocimetry. We're zooming in inside this blob over here to get a reasonable resolution. And then we're plotting over here the energy spectrum, so how the energy is distributed across different wave numbers. And this is from a single shot. And this is sort of showing you how it evolves in time. So all I want to really say from this movie over here is I'm not claiming any power laws or anything. I want to sort of show that it is broadly distributed, right? So that's kind of promising. It's oscillating up and down a little bit, depending on the forcing, which is to be expected. But the main point is that it's sort of broadly distributed, and this sort of looked promising to us. If you average this, you get something that looks like this. If you average it in a phase-resolved way, so we're forcing this by shooting rings in. If you measure everything with a fixed delay from when you shoot the rings in, then actually this spread goes down, and essentially you get a single curve like this one, which stays the same. I'm not showing it over here, but that's good to know. So how can we relate this to turbulence? So the sort of central tenet, or at least in hydrodynamic turbulence textbooks, the first thing that you read is that the thing to that characterizes turbulence in a viscous incompressible fluid is the energy dissipation rate. And if you have an idea of the energy dissipation rate, you can then go ahead and de-dimensionalize all the quantities that you have in your problem. And so in particular, you can compute a dissipation scale, Kolmogorov length, and you can de-dimensionalize your wave number using this Kolmogorov length, and then you can de-dimensionalize your energy. And so the idea is that if you do this, if you have a value for epsilon, you can then simply take all your experiments, and this is a image taken by a review by Sadugi and Beravalli, in which they took lots of different experiments and did this scaling, and you see this sort of collapse on this master curve. And so this is what we had, and we needed an epsilon. And so we decided to be optimistic and say that all the energy of the incoming vortices is going into turbulence. This is a steady state. Therefore, the value of epsilon should be 8 times the energy of a vortex ring times the frequency of injection. Right? And then this should be the energy dissipation rate times the density times the volume of the blob. And so we can sort of characterize these things well because of the vortices are sort of amenable to that. And what we found when we did this is that our measured spectrum fell quite nicely on this curve over here. Yep. Oh, 5 minutes. Okay, thank you. Okay. So we thought this was sort of promising, and we still think this is promising. This is work in progress, but we'd like to have discussions about this. Other things that you can measure, particularly if you're measuring in real space, are things like the correlation functions, the second-order correlation structure factor. This is a sort of not quite a universal curve because its shape depends a lot on the Reynolds number of the flow. This is what we measure inside our blob, which is a lower Reynolds number from this master plot taken by Sadugi and Beravalli. But again, we think it looks sort of reasonably suggestive of a turbulent state. You can then go and calculate all the other quantities. And again, this is work in progress, so I'm up for discussion of all these numbers. But we think that there's sort of some strong evidence or some strong suggestion that what we have inside this blob is a sort of nicely self-confined turbulent blob-like state. You can compute, this is just computing additional quantities. So what we're trying at the moment is we're trying to see, okay, we think we have something that looks like a turbulent blob. What determines its properties? Can we change its shape? Can we tune it in some ways? And so we're trying things like changing the size of the vortex rings that are coming in the same tank. And what we find is that we can sort of actually reduce the size of the blob roughly from the size of the ring. So there's a strong connection between those two. And then, of course, the other thing which we're trying is to inject helicity by creating, sort of evolving a technology for making vortices to this sort of setup and injecting helical vortices in order to try and control the helicity injection inside this tank. So, so we're sort of excited about this transition to this confinement state. And one of the things which we're finding is that once we've sort of started thinking about this and playing with this, we started with the idea of doing this from the point of view of helicity. We found that actually we have a different way of making turbulent and spatially inhomogeneous turbulence, and this could be useful or interesting to address a lot of problems. Right? Which ones we're still honing in on. But one of the problems that this system seems particularly suited to relates to the question that Mike asked earlier, which is what happens if you stop forcing it and let it go? Right? In many experiments in which people study the decay of turbulence, the turbulence is being advected. Here it's just sitting there, so you can just watch it. And so let's watch. So this is what happens. Now, I didn't rescale the energy distribution. Let me rescale that energy distribution, and this is what we saw. So we see an immediate sort of expansion like dynamics, and then on a longer time scale, we can sort of see the formation of some sort of coherent structure that's left behind. Because this blob sits there, we can actually measure its evolution of the energy density over long time scales, and we're starting to see our first indications of sort of maybe some quantifiable and reproducible behavior, which we're sort of very excited about. So I think I can see the chair's getting nervous. So let me conclude. First of all, let me acknowledge everybody who did the work in the vortex dynamics. This was really the work of these people over here. Bob Morton, who's a graduate student, Dustin Kleckner, who was sort of really started all this stuff off together with me, and is now a professor at Merced. Hridesh Kedia, who's a graduate student, currently at MIT as a postdoc, and Martin Schieler, who did a lot of the second part of those experiments and is now at Boston Consulting. And for the second part of this talk, the sort of person who really did the heavy lifting of everything I've shown you is Takumi, who's in the audience somewhere. There he is, okay. And Noah Mitchell and Stefan Perard, who helped in the early stages, and of course Nigel Goldenfeld, who's been talking to us, sort of stimulating us, and with whom we've started a collaboration to try and understand and get to the bottom of what's interesting to do with this turbulent blob. Okay, thank you.
We can take one or two questions.
Yes.
So, but Lexi?
Really beautiful talk. I'm curious to know if there's any plans to do these kind of experiments with fluids that are either compressible or less viscous fluids, right? So you get a larger inertial range.
That would be very nice. In particular, of course, the dream is always to go to superfluids to get really nice separation of scales. Other than flirting with the idea, no concrete plans. But it is, especially in the superfluid case. In the compressible case, I'm not sure if we're the right people to do it. In the superfluid case, we're sort of thinking about it. But that involves a bit of infrastructure.
For the quantum turbulence,
yes.
When you have vortices that are of the order of a molecular diameter, you think the reconnection will be very different somehow? And what happens to helicity even if you inject it ahead of time? So you don't have strands in it, presumably.
Mm-hmm. So there were a couple of questions there. I think one question was in superfluid vortices, if you go to very low temperatures, the reconnection dynamics can be a little bit different. And the other one is, everything I've shown you over here with these pictures of tubes, which remind you of discrete vortices, but of course, vorticity is a continuous distribution, and how does that change things? So I'd say I'll address the latter question first. So I've used those tubes as cartoons to illustrate the ideas, right? But what I was actually doing was sort of differential geometry, and behind each one of those cartoons is actually a continuous statement that you can make about a continuous vorticity distribution. These tubes don't need to be discrete, they don't need to exist, and they don't need to close after a loop. They're a representation of the differential geometry of the vorticity bundle. So all those statements carry across in the absence of discreteness. As for the reconnections, I'd be interested to know more about what the current state of the art is in the quantum reconnection. When I looked at this a while ago, the sense that I got was that there are important differences, but they don't change this fundamental ingredient of the reconnection being locally anti-parallel if you have a good separation of scales.
Yeah.
And that's the only thing which we need.
Yeah.
Yeah, very beautiful experiment.
Thanks.
One simple question. In the proper physics, helicity conservation is not really challenged. It's more energy. So reconnection is used to destroy energy in magnetic fields.
Mm-hmm.
Or this case would be flow energy. You have the E there.
Yes.
And wondering if you quantify energy evolution as compared to helicity evolution, you have to quantify.
Right.
Are after all this?
No, that's an excellent question. So one which when we were doing the reconnections, we weren't able to resolve the kinetic energy. We didn't have this sort of PIV technology working. So we addressed that at the time by looking at just the energy inferred from the vortex shape. And in that case, the energy is a little bit more conserved than the helicity, not much, but a little bit. But you should take that with a real pinch of salt, because we really were not resolving most of the energy dissipating phenomena and a lot of the helicity dissipating phenomena. So I think it's an interesting question, which we should go back and look at now with these slightly different techniques.
Do you care to speculate on applications of your work for magnetized turbulence by analogy?
I'm hoping you would. I mean, I've always had this sort of, if you like, dream of maybe understanding a little bit better how, plasma physics and educating myself. I prefer not to speculate in general. I think that one statement that we sort of heard already is that one of the things that's attractive about plasma physics in the context of helicity is that there's a sense that I get from the community that it's more conserved somehow than it is in this case, and it's more important in determining the dynamics. But again,
doesn't that just depend on its viscosity or resistivity?
Yes, that'll depend on the parameters. But at least in hydrodynamics, I'd say we don't yet have a smoking gun of where helicity is more important than energy. And I get the sense that in plasma physics, at least there's some area of phase space, maybe tiny, in which this might be true.
Have you considered using liquid metal?
Yes. Considered, and I think I'll leave it there.
Very beautiful talk. I just had, it seemed to be that you were associating all the energy that was coming in through your vortex rings to being dissipated within the blob. Mm-hmm. But when you showed early on, you showed propagation away from the blob. You would have thought that there'd be substantial energy being affected away. Is that not the case?
Not as far as we can tell. But as I said, we're sort of refining our measurements. We could be off a little bit in our measurement of the energy of the vortex going in, which would then suggest that there's a constant energy flow out. But most of it is staying in there. Right? There's that interface is fairly sharp. It's sort of Paolo-like. It's fairly sharp. Let's leave it at that. And we don't see evidence of this as far as we can tell.
Okay, I think obviously it's a very exciting talk, and there'll be a lot more questions, but there are lots of breaks and discussion, time for discussion, so maybe we can carry that on to there and let the second speaker speak. Thank you.
Thank you.
Okay, so now I would like to go from the 10 centimeter scale to 10 to the 19, 10 to the 20 centimeter scales, and talk about some things that myself and my colleagues have been working on in terms of statistics that are going beyond the power spectrum, beyond like 1-point, 2-point functions, and really what can that do for not only astrophysics, but potentially interest all of us here in the room. So I'm going to start my talk with my summary, with my conclusions, and these are the basic points I want you to take away from the talk, is that for the astrophysical perspective, we have turbulence. It's present on a huge range of scales in galaxies, from sort of solar system scales all the way up to thousands of light year scales in galaxies. We know this because we observe beautiful power spectra over these scales. We have high Reynolds numbers, etc. So it's there. It's also important for a wide range of physical problems that astrophysicists find important. One challenge for this field, though, is that because we have only line of sight information, right, in terms of our velocity and density statistics, we need to be very careful how we study astrophysical turbulence in terms of the statistics we use. And so I think there's a lot of exciting progress that's been made here. There's a lot of now open source statistical toolkits and simulation sharing projects, which might not only interest astrophysicists, but also people in other communities. And now, of course, combined with machine learning approaches, I think this is going to be a really exciting, steps forward. And I'm quite excited to see what you guys are also up to. So this is a summary of the talk. These are the takeaway points. So I think about turbulence in terms of a wide range of problems that astrophysics care about in galaxies. And this can go from things like the process of star formation and the interstellar medium of galaxies to solar systems, to the process of reconnection in terms of magnetic reconnection. We see this happening all the time in the sun, causing solar flares. So this is also generated and mediated by turbulent motions, somewhat similar to what William was talking about, but the magnetic version of it. So there's all these beautiful problems here to try to understand, but we can't really get a strong understanding of the physics of these different aspects of galaxy evolution and formation without understanding how turbulence mediates all of these processes. And so this is a really big challenge for this field. And people have really, I think, started recognizing this challenge is important. And I was playing a little bit with looking into the literature since the 70s. The number of papers that mention turbulence, these are just from the astrophysical perspective, the astrophysical literature, in the abstract in one way or another has grown. And now there's more than 300,000 papers that are talking about the importance of turbulence in astrophysics. So this is actually a major challenge for this field. Why do we think we have turbulence in galaxies? Well, fluids naturally, of course, present themselves as turbulent when you get to high Reynolds numbers. So the Reynolds numbers, if you just do like a back of the envelope calculation for a star forming region in the galaxy, with the typical length scales and velocities and small viscosities that we deal with in these sorts of fluids, we can easily have Reynolds numbers of greater than 10 to the 10. So just naturally from that kind of back of the envelope estimation, we would expect these clouds to be quite turbulent. We also see evidence for turbulence in our observational data. So here I'm showing an example of this beautiful all-sky map that was produced by the Planck satellite. And there's many interesting science topics to study with this map. One aspect is the turbulent and somewhat chaotic features that you see in these magnetic field line vectors that can only be explained really with statistics of turbulence. And so I won't talk about that in detail, but just as a beautiful example of a turbulent flow in our galaxy. We also can directly measure the power spectrum. I say directly measure, but really these are indirect measurements from observations, because again, we have only line of sight information, but at least we can estimate the power spectrum velocity. This example here is showing electron density fluctuations from a variety of different measurements. And you see this beautiful 5/3 scaling law over many orders of magnitude in scale. And so this is one such example, this sort of big power law of density fluctuations that we have a turbulent ISM and that we deal with turbulence in our galaxy. So again, the complication not only is from the observations, but also from what we expect theoretically. So we don't expect just one nice, clean injection source of turbulent energy. We should have multiple injection sources coming from a variety of complicated astrophysical processes. So on the largest scales, oopsies, there's parsecs. See, I didn't fix it all. So, thousands of light years scale, this can be easily supernova, expanding shells, some sort of different instabilities that could be mediated either by fluid instabilities or gravitational instabilities or magnetic instabilities. And then going further down the scales, we can even have aspects like stellar winds, outflows from stars, et cetera, that drive turbulence on sort of solar system type scales. So a variety of different types of drivers. In terms of which of these drivers is probably dominant in the interstellar medium of galaxies, likely it's supernova. And again, one can do that in a very back of the envelope type of way where we just estimate the energy output of these different astrophysical processes. Supernova come out on top. So they're likely one of the main drivers of these turbulent motions, this power law scaling that we observe in galaxies. However, this is still an active area of research. What drives turbulence in galaxies and solar systems in the interstellar medium? Some recent work I just wanted to highlight by a student that's been working with me Monica Gallegos. She's been doing numerical simulations, putting in stars of different stellar type that have different outflow properties, different wind amplitudes, and showing that these stars can very easily and very quickly, in a few thousand years, drive a Kolmogorov-like scaling in velocity in their surroundings. And so it's not only the supernova that can drive turbulence in the interstellar medium, but also the stars themselves as they live out their lives and inject energy into their surrounding medium. So that's a little bit about where the turbulence comes from in astrophysics. Now, how do we study it, right? Because again, the complication is we only have all this information coming to us from the line of sight. We can't actually set up a beautiful experiment and study in real time how the turbulence develops. And so we really have to take a holistic approach where we combine our numerical simulations, similar to the one I just showed a highlight from Monica, theoretical predictions, how the scaling laws should behave, how the different statistics under the influence of turbulence should look as a function of time. And finally, of course, our observations, right? So our data, which will either confirm or deny our theories, and our numerical simulations are actually showing us something that we expect. And I think this is really how we have to study turbulence, perhaps not just in the astrophysical context, but also in the context of other interesting problems that deal with turbulence as well. How do you do a crosstalk with these different avenues, right? These different approaches, right? How do someone that does the observations, how do they talk to a theorist? How do they talk to someone who does numerical simulations? Or how do we, as people coming from different communities studying turbulence, how do we talk to each other? How are we going to discuss our problems at this meeting? I think a common linking point will be and can be the fact that we all use a statistical language to talk about turbulence, right? We talk about turbulence in terms of scaling laws, in terms of different aspects, 1 point, 2 point, and even higher point statistics. And that can be the bridge between not only our different communities, but also even sub-communities that are working on the problem of fluid turbulence. And so this is where I think the bridge can be with statistics. Now, for the remainder of the talk, I want to talk about turbulence statistics. And the punchline here is that we're really thinking of statistics now kind of beyond the traditional power spectrum, beyond the traditional kind of maybe PDFs or structure functions or correlation functions, 1 and 2 point type statistics. And we're trying to broaden our horizons either with higher order statistics or potentially with machine learning algorithms. And I think that will be kind of a big aspect of today's talks. So one thing that I basically spent my PhD on was developing different statistical diagnostics for the application to observational data to find out turbulence parameters. So for example, in turbulence, we have highly compressible fluids. And so we need to know things like the sonic Mach number of the flow. And that's an important parameter for a variety of different problems. For example, star formation, right? Star formation takes place in fluid flows that are extremely compressible with Mach numbers of around 20 or so. So there's a variety of different statistics that can tell you not only about the properties of the turbulence, but maybe also the sonic Mach number, right? So the power spectrum, for example, as applied to something called a column density map, can tell you about that Mach number. There's other parameters of the turbulent flow that are interesting for astrophysics. For example, because the fluid is magnetized, then we have to apply the MHD equations. And an important parameter there that describes the ratio of the turbulent kinetic energy to the magnetic energy is something called the Alfvén Mach number. And we've also been developing some statistical diagnostics to try to obtain that Alfvén Mach number from observations as well. So this is the general landscape. And now I want to talk about, well, why would you even bother developing these new statistics, right? Aren't 1 point and 2 point statistics good enough, right? People have been using power spectra, correlation functions, structure functions, PDFs forever. Why would you care about developing new statistics? Well, this is what I want to show now. So this is, for example, a 1 point statistic, right? Just a histogram, a density PDF. And the movie here is showing a driven, compressible, turbulent box. And I'll try to go back and play it again. There we go. So it starts with a uniform density distribution. We continuously drive turbulence on large scales in these types of boxes. And then on the right is showing the corresponding density PDF. So these are simulations done with a code called Flash by Daniel Price and Christoph Federath. But basically, there's many different communities that are doing turbulent box simulations like this, and they all get the same one-point statistical result, which is that the density PDF is this nice, clean, log normal distribution. And this is what you expect in the limit of compressible turbulence with high sonic Mach numbers given interacting shocks and the central limit theorem. So the nice thing for the observations and for our simulations is that as we increase the Mach number, basically that just drives this one-point statistic width to larger and larger values. So here I'll show you an example with some simulations I've run. So this is a Mach 0.5 simulation, so it has a low sonic Mach number, and the density fluctuations, therefore, are quite weak. And so you have this log normal form, but it has a very narrow width. And as I increase the Mach number, I just simply broaden that width in my one-point statistic. So I'm just running new simulations with higher Mach numbers. You get these beautiful shocks that form that increase the density contrast, and then you just go towards higher and higher widths. Okay, so this is quite nice and well understood, but there's a problem here, right? Because you're not capturing any structural information in this turbulent flow when you look at a one-point statistic. And here's an example of that. So you can take any sort of image, so a turbulent image or an observation. Here's an example from Eric Koch with Rho Ophiuchus, which is a beautiful star-forming cloud in our galaxy, and its corresponding PDF. Well, there's no structural information in that PDF, so I could scramble all the pixels around and basically take all the pixels, just scramble them spatially, and it will look like noise, but it has the same PDF, right? Because the PDF is just sensitive to the fluctuations, the intensity fluctuations. Well, you can do this actually for any image. So you could even do it for Jim Simons. So you can take an image of Jim and normalize it and then scramble the pixels or not scramble the pixels, but basically you can provide a particular PDF form and then renormalize any image you want. So this could be done, of course, with Jim, for example. So this shows you that basically the PDF, while interesting perhaps in terms of some sorts of diagnostics like the Mach number, is not telling us anything about the structure of turbulence. All right, well, of course, then we can go to a two-point statistic, right? So like the power spectrum of velocity and density, this is nice because it tells us more about, of course, the structure of the map, the energy flow, or how the density is getting structured. And there's nice analytic predictions for how our two-point function should look, right? So for example, with velocity, we have a Kolmogorov slope. These are simulations that are compressible, so we still in velocity have roughly a minus 5/3 slope. In density, the slope becomes shallower because we start building up shocks which act as delta functions, flattening our power spectrum away from 5/3. So this is actually nicely understood both analytically in general and for sure with the numerical simulations. From the observations, we also can go out and measure our velocity power spectrum, right, from our 1D Doppler shifted velocities. So there's some difficulty there in terms of what is an object and how we're measuring that, but we're able to do it for certain objects. And then, of course, the density power spectrum is a little bit easier because we can just measure that directly from intensity maps. And we generally find, the punchline here is that the velocity index is roughly Kolmogorov. That's what we observe in various regions of the galaxy and different tracers. The density power spectrum, however, is significantly flatter, right? But again, that's what we also expect for compressible supersonic turbulence. And so this observations kind of agree very nicely with that picture. Well, but how robust is a two-point function, right? Is that giving us all our information? And I really like this example from James Beattie. James, I think, is here. Yeah, there he is. So James did a really cute study where he took Van Gogh's Starry Night, which, you know, you could maybe argue that this is turbulence from a structural artistic point of view, but James actually went off, took a slice of this, and measured the 2-point function, measured the power spectrum, and found that it was basically very similar to type of Berger's turbulence, compressible supersonic turbulence. So if you'd taken, Van Gogh's Starry Night, just looked at its power spectrum, you'd be like, like supersonic turbulence. So it's kind of ironic because astronomers, especially theorists that do turbulence studies, all the time love to show this image as their example of turbulence. But indeed, it has a supersonic turbulence slope. That's it. The Dutch. Yes. So I think this is kind of a smoking gun that, while the power spectrum, of course, is extremely important for studies of turbulence, we need to go beyond, right? We need, in particular, to have a statistic that's sensitive to phase information in the maps, which the power spectrum, of course, is not. And so this is our motivation now for going out and looking at different statistical tools, things like a higher order power spectrum, like the bispectrum, which is a 3-point function that depends on phase information, tools that depend on topology, which is the genus. An example of that could be like a genus type of statistic, hierarchical structure statistics, for example, a dendrogram is an example of that. So these are just some possibilities, and I'm quite curious to see what everyone here is doing. In my last couple minutes, I'll just mention a few advertising type points along these lines. So I think neural networks, which will be a big topic for today, are going to be important for this, and in part because they are very sensitive to phase information in the maps. This is an example of a study that was done by Josh Peak and myself in terms of looking at simulations of magnetized turbulence and running them through a neural network to see how the network is learning different types of features in these maps. So the network is able to identify different types of parameter space in these maps extremely accurately, but we were also curious as to how it was doing that and why. It turns out it's very sensitive to phase information in the maps. So when we removed the power spectral information, basically the maps were the network was still able to pick up these features. And so we understand that it's learning by the phase information, but there's a lot more interesting work to be done with this. Some advertising points, and then I'm finished. I really am excited to work on collaborative aspects of turbulence, not just with the astrophysical community, but also with all of you. And so we've started a project called CATS, the Catalog for Astrophysical Turbulence Simulations. But I think many of these simulations might even be broad enough to be useful for different communities. They're hosted at mhdturbulence.com. You have no idea how happy I was when I got that domain name. I was like, yes, I can't believe you guys didn't get it yet. Haha. So go to mhdturbulence.com and you can find, it's basically still a work in progress, but we're already starting to link a lot of different simulations with different codes. Another advertising point regarding the statistical tools is that there's a Python-based package called Turbustat that's available. It's particularly designed for astrophysical observables and applying these different statistics, but all the code is open source, and so you could basically take the statistics and rework them to your purposes and actually and contribute to the project as well. So here's the link to that, and I can also, if you're interested, email you more information about this Turbustat package, which was developed by Eric Koch. Okay, so I'm finished. You've already seen my summary, and happy to take a few questions.
And maybe a comment. The question is, in astrophysical turbulence, is there a way to separate the solenoidal from dilatational component at all? I think it makes a huge difference to how you understand what happens. And the comment is that, in fact, if you go to 3-point statistics, let's say around the vertices of a triangle, you can show how it is sensitive to the structure, unlike the two-point statistics. And it can be done very successfully for passive scalars, and I don't see why it can't be used for
Yeah, you could
astrophysical
definitely, I
things.
mean, so for the point of view of the simulations, you can absolutely do that. From the observations, basically all you're able to look at is gradients. Because you have the 1D, yeah. So with the simulations, it's possible to do that and maybe make some observational signatures of that. So that could be very interesting.
Yes. So, okay, so first of all, the slide that I show MA, alpha Mach number, I think you may also want to add velocity gradient as another measure of alpha Mach number.
Yes, absolutely. So yeah, that's, I think, will be discussed also.
Yeah.
There'll be some talks on that, but yes, you're right. I should add that to the slide.
Yeah, and I have a question that, you say for supersonic turbulence, and I see this observation still show cosmograph velocity spectrum, but some simulations, they suggest that in supersonic turbulence, the velocity spectrum should be Berger spectrum. What is your comment on these differences?
Yeah, that's interesting. I mean, I think from the observational point of view, we're getting something closer to the 5/3 slope. And also in the simulations, we see basically that the slope isn't that changed in velocity in terms of the simulations as a function of Mach number. So yeah, that's something I think we can discuss further.
Okay, I think go on to the next speaker.
Oh, thank you. Yes, I'm Philip, and today I'll talk about the compressible aspects of turbulence. So we've heard great talks so far about the incompressible properties, for example, of helicity, and we heard great talk about statistical aspects of turbulence. So now we're going to focus in on some of the physical structures for compressible turbulence. And so here are two slides where I'm going to describe two different aspects. I'm an astronomer, so this is in the context of star formation, but I'm going to apply a very simplified theory where that's missing a lot of astrophysics, so it's probably good for this audience. And so on the left, we have a formation of a prestellar core in a simplified system, and you can see, for example, this is a density slice, and you can see one of the structures is a shock. And we're going to describe the properties of such shocks. And on the right side is a simplified one-dimensional model for turbulence, which I'll talk in the second half. The context here is supersonic isothermal MHD turbulence. So these systems are characterized by three parameters, which we heard from Blakesley. One is the sonic Mach number. So for systems for star formation, this can be around 10. The second one is that if you put in a magnetic field, then the alphanic Mach number also characterizes the system. And finally, if you have self-gravity, then a third parameter might characterize the system, called alpha. And so this system, if you stir it, you give rise to complex behavior, turbulent structures, etc. And this is a simplified model for studying star formation or really any turbulent system. And there's just one of the big assumptions here is that we have isothermal equation of states. So energy dissipation does not lead to heating; it just gets immediately radiated away. But you can change this assumption if you like, and many of the qualitative behaviors that I'll talk about today stay the same. So just for the astronomers, I just wanted to motivate the isothermal model where there's just the pros and cons, where there's lots of observational evidence for why this system might be sort of realistic, such as when one goes out and measures line widths in molecular clouds. There's also a bunch of radiative collisional heating and cooling processes that keep the gas at approximately 1 temperature. And then some of the weaknesses are that it ignores some of these complicated astrophysical phenomena like feedback, radiation, chemistry, coupling to large galactic scales. but I think that's a pro for this general audience because we can just work with a simplified model today. So in this talk, I want to go beyond the common statistical or Fourier space descriptions, like what we talked about, what we heard in the talk about Blakesley, talk from Blakesley today. So go beyond 1 and 2 point statistics, and particularly I'd like to work in physical space today and talk about the dense structures that form in turbulence. And then in the second part of my talk, I'll talk about the simplified 1D Markov model to describe some of these density structures and their evolution in time. And so part 1, the dense structures. So it turns out if we stir one of these turbulent boxes on large scales, it develops this system of turbulence. It develops a turbulent cascade. We can go in and identify where are the densest regions in this box. And this is interesting because in the context of star formation, it's going to be these dense structures that collapse and form stars. And so we can show that the densest regions are these. They're actually shocks. They have a density jump that scales as the Mach number squared. This is well known. And one of the interesting features that has been recently identified is that they, in the context of isothermal turbulence, they form these exponential profiles, shown on this second panel here, where you can derive their shape by balancing the upstream ramp pressure with the pressure gradient behind the shock. And on the third slide, we can see this velocity jump that accompanies this shock. And so this is a simplified cartoon of what's going on now in the context of magnetic fields, where you have these strong quasi-1D network of shock sheets. And if you add in self-gravity, it's these sheets that collapse and form prestellar cores. If you add in magnetic fields, then these sheets perhaps might be aligned with the magnetic field because it's easier to compress material in that direction. So I'll talk about that a little bit more on that statement in the next couple slides. And so in the context, these sheets, they sweep up material, so then they slow down and they expand. Their expansion time scale is roughly the crossing time of the stirring length. And if you compute the gravitational freefall time of this gas, it's also comparable. So these transient structures can sometimes collapse into stars, sometimes not. It might say something about the inefficiency of star formation, which is observed by astronomers. And so now a little bit more on the statement with magnetic fields. On the left, I'm showing two cases where I'm pushing the gas just in one dimension. So if you go parallel, if you push parallel, then these shocks look very similar to the hydro case. You have these strong density jumps that it goes as the Mach number squared, and an exponential self-similar profile. If you push perpendicular to the field, then the density jump is reduced, and these waves expand much faster at the fast magnetosonic speed. These are just two cases. You can, of course, have oblique shocks, etc. But based on this cartoon, you expect that maybe collapse perpendicular to the strong magnetic fields might be suppressed. And so star formation might happen in a geometry of parallel shocks. And so, so we studied this in simulations where we drive turbulence. At some point, we can switch on self-gravity, form prestellar cores, and really look into the structures that form. Again, this is just showing a zoom in of what happens after gravity is turned on as a function of magnetic field strength. When you have strong magnetic field strength, these structures do tend to be aligned parallel to the magnetic field. In the case of weak magnetic fields, these structures are sort of decoupled from the global magnetic field strength. So we went into the simulations and identified all the densest fluid gas cells in the simulation and stuck skewers along the direction of the density gradient and found that they're all associated with these strong exponential-like, so these strong shocks with exponential-like profiles that expand for that they extend for 1 or 2 scale heights, And so here on the top, I'm just showing it for the simulations with the varying magnetic fields. And this picture is perhaps the clearest in the strong magnetic field case, where the magnetic field helps stabilize these structures. So they have the largest range of extent. So they extend maybe for 2 scale heights. And we found that the dense part of the log normal density PDF is made up entirely of these exponential atmospheric shocks. So why is this interesting? Well, so we went from a global system of supersonic turbulence, and we identified these subsystems that are stratified. And so pressure is really playing a role in reducing the degree of freedom in one direction of motion. And so now we can, so there's interesting follow-ups where we can think about what are the turbulence properties like in these subsystems. And so, yeah, so just one slide on what happens to these shock sheets. After you have self-gravity, they become isothermal cores. So they have R to the minus 2 density profiles. But so future questions we're investigating, and yeah, there's a poster outside by Mike Foley. Is how do these questions include? So how does turbulence in these dense post-shock regions compare to the overall Bach statistics? And so, for example, you might expect stratification might produce inverse cascades, maybe 2-dimensional turbulence in the post-shock region. And again, we want to understand also the velocity power spectrum, and whether it's more like Kolmogorov or Berger's turbulence, just in these restricted to these subsystems inside the turbulence box. So I wanted to talk about 2 topics today. So the second one is just a simplified Markov model for these density structures, these strong shocks that I've mentioned. There's transient structures. They form and decay on this stirring time scale, the eddy time scale of the stirring scale. So just to list the equations that we've been dealing with. So in units where the sound speed is 1 and the average density of the box is 1, and I've defined S as the log of the density, then the equations for isothermal fluid dynamics in the simplest case are without gravity, without magnetic fields, are just equations 1 and 2, where almost look symmetric. So changes in density are entirely just caused by compressions. And there we have the equations for the momentum equations in the second, in equation 2, where F is a stochastic forcing term to drive the turbulence. And equations 3 and 4, I've just highlighted these in 1 dimensions. And so one of the aspects of this equation is that we've heard discussion on the 1D on the 1 point statistic, the power the PDF, the probability density function of the density, and we've heard that it's log normal, and that sort of comes from just looking at equation 1 and saying that maybe on the right-hand side, this divergence of the velocity field acts like a random variable, and by the central limit theorem, then S should be distributed normally. So that's where this log normal comes from. But we're going to go into more detail that shows that that's not entirely true. So we can think about this framework of describing changes in the density using a Markov process, where there's basically 2 terms in this process, and there's only one way to get an exact log normal density distribution. So there's an advective term and a diffusive term. So advective will say that on some evolution timescale, tau ev, the density local fluid parcel will lose memory of its density, what it used to be. So you might expect maybe this this loss of memory occurs on the crossing time, for example, or the eddy time. And then secondly, there's a diffusive process characterized by D. So you can go into the simulations and locally track how the density at the current time for a local fluid parcel correlates with its density previously. And so at time, so this is what, these plots here are showing just that. So at time t equals 0, this memory, it correlates with itself perfectly, so this line should just be flat. If you have, once it loses its memory entirely, this slope has, this line has a slope of 1. You can see that as time progresses, it approaches 1, this slope of 1, for all these supersonic Mach number simulations. But you can see that on the high density end, it starts losing memory faster. So the dense structures are, really the different structures than the low density structures and evolve on different timescales, even though you have this log normal distribution in the density PDF. So let's look at this in a bit more detail. So with a 1D model, so where we can run 1D simulations of the shocks and fit a Markov model, and then ask how well does this model explain three-dimensional simulations. And so if it does well, then the role of helicity, for example, might not be important in describing the density field. And so we can also ask whether shocks dominate these really high Mach number regime, or whether turbulence dominates in the dissipation. So this is really a comparison between what's known as turbulence, which is maybe the Kolmogorov regime, and turbulence, which is this shock-dominated regime. And so these are just 1D simulations, space-time diagrams of the density field and the velocity field, showing the generation of these shocks. And we can look at the density field and fit a Markov model, looking at how the density of a local fluid element correlates with itself. So we found a simple phenomenological fit to what we measured in the simulation, described in an equation state that describes the high density gas losing memory more efficiently. And we actually find, when we do this very carefully, we make a prediction for the density PDF, which is not quite log normal. It has some skewness to it. And when we compare this to really high resolution 1D and 3D simulations, we find that this 1D model, Markov model that we tuned to just 1D simulations, actually describes the 3D simulations quite well. If we just, in the 3D simulations, we have to replace just very simply the Mach number with just the compressive component of the Mach number. So this is really interesting because in a way, the compressive and the rotational nature of the fluid is sort of decoupled when you're just thinking about describing some of these 1-point statistics of the density field. And so, here are just predictions for the PDF moments, showing how the model is negatively skewed. The variance roughly grows linearly with Mach number. So it's sort of different from some of these earlier models that oversimplified the density PDF as just a log normal. And so if you apply it to, for example, predicting the star formation efficiency by saying that maybe gas above some critical density all collapses on a free fall time and forms stars, then the efficiency is increased by maybe a factor of 2 compared to just the simplified log normal model. And so in conclusion, when you look at supersonic turbulence under the microscope, shocks, these stratified atmosphere-like structures, are really important for star formation. And also you can think of supersonic turbulence as really almost these brick walls of quasi-1D shocks slamming into each other. They make up most of the mass content, but really have a very small volume filling factor. And so, supersonic compressive turbulence is really the system of interacting shocks, where you can then go in and look at the post-shock properties and maybe treat that as a subsystem and look at turbulence there. And this subsystem is going to be sort of like an atmosphere which describes oceans or the Earth's atmosphere because it's stratified. And so in the case of magnetic fields, which are important for the interstellar medium, magnetic field helps align and stabilize some of these dense structures. And finally, point 3 is that this 1D Markov model can be that we really use to characterize one-dimensional burgers like simulations can be used to describe the non-log normality of the density PDF in fully 3D compressive turbulence. So that concludes my talk, and I'm happy to take some questions.
Let's do time for one very short question.
We should definitely chat later because I've been doing some similar work recently. I was just wondering, in your 3D simulations, do you actually find that your shocks are aligned or co-aligned with the, perpendicular parallel with the magnetic fields? Do you find that?
Yeah, if the magnetic field is very strong, then so if you have some large global mean field in your box, then you find pretty good alignment with the densest structures in the box. Yes.
Okay, let's take this.
Good morning. Okay. So this talk is in collaboration with with Abbas Ormus from University of Wisconsin Milwaukee. I'm affiliated with, as well as Dimitris Giannakis from Curran Institute and Jörg Schumacher. Both Dimitris and Jörg are here today, and they are experts in turbulence and dynamical systems, and they strongly contributed to the talk here. So when we talk about turbulence, we can think undoubtedly about pattern formation and spatial-temporal coherent structures that are ubiquitous in nature, starting from very small scales, reaction diffusion type of system, to give an example, through type of scales that would be very much at the center of our work that we focus on, which is turbulence in the Earth, atmosphere, or the ocean, to larger scales such as cosmic scales. We have been mainly focusing on the geophysical applications. However, we experimented with other applications such as biophysics or neuroscience. Astrophysics is on our agenda as well, since we have some background in astrophysics, including convection in the sun or pulsations and magnetohydrodynamic interactions. And the issue is that we, for all these fields and these applications, one can notice increase of data sets of good quality, even coming from observations or from simulations that are getting better at capturing the complex nonlinear features that cannot be otherwise explained simply by some numerical models. And because of that, there's also a lot of interest to take advantage of that, especially given the fact that there's a lot of new tools coming in from artificial intelligence type of research. So to give an example how traditionally people try to extract such spatial-temporal coherent structures, I'm giving here a little bit of overview of some approaches. Many of them focus on deal with and extract relevant features by again decomposition of operators that act on some space of temporal patterns. Here are some examples of classical approaches such as POD or PCA, which are covariance-based operators, or SSA, which is a covariance operator based on in delay embedded space. Other type of operators that gain some attention are heat operators or Koopman operators. And again, the composition of these operators allows us to get temporal patterns. And the question how one associate spatial patterns with given temporal patterns or we get is somehow independent. But the way usually it is done is through a projection of temporal patterns onto raw data, onto pointwise projections. And in the essence, doing some type of obtaining some type of inner product and or time average. And so, in the essence, what happens? In order to extract or reconstruct our signal, we have a framework that is based on tensor product of separable space and times patterns. So this can be okay for some applications. For other applications, especially turbulence, very often it fails badly, and it doesn't capture or it doesn't deal optimal with issues such as symmetry or spatial temporal intermittency. And other important aspects in general when dealing with physical applications I have been showing as an example in turbulence is that this type of statistical approach does not really allow one associate underlying dynamics very easily and interpret the dynamics associated with that. So that's the problem. So people try to look for new methods that that would deal with that, especially coming from machine learning type of approach. And and this is just an example of how badly classical example can fail. So here I'm showing some raw signal, which is just a simple traveling wave coming from Kuramoto-Siwasinski in simulations. And when we do POD type of decomposition and then reconstruct the signal, we can see patterns on the right side that we get, which are totally not informative when it comes to traveling nature of a signal, as well they are not optimal in terms of the number of modes we get and what we do with them afterwards. And here there's another example we have been focusing heavily, and I will be referring to later in the talk, which is more complex example of Kuramoto-Siwasinski with a regime, which is a prototype spatiotemporal PDE for chaos and intermittency, and it also has translational symmetry. And the raw signal is shown on the left. It's a spatiotemporal Hofmüller diagram. And then if we obtain temporal patterns through PCA type of analysis and then reconstruct the signal, we get a family of modes on the right side that are nowhere informative in terms of the dynamical nature of the signal. Namely, they mix scales and fast and slow scales of the signal, and they also spatial patterns are just simple Fourier type of modes that are narrating. So the group I'm working with is focusing on exploring operators that are associated, that actually govern the temporal evolutions of dynamics. And this is the simple setting that one is having in mind when trying to take advantage of these operators. On the left side, we have a framework for dynamical system that goes through a sequence of states and evolves in time with some dynamical map that evolves underneath. And the goal is to derive temporal observables that are on the right side that would be associated with dynamics and associated with the phenomena of interest we are interested in. So we approximate and dynamical operators that afterwards one would hope would be useful in terms of analyzing the data sets. So one would want to get some type of analog of PCA. However, instead of covariance operators, decompose dynamical operators. And what is in principle attractive about that approach is that dynamical systems are well known, so there's a huge machinery behind it of concepts that could be useful afterwards to interpret the results. And provide insight into the field of turbulence, including instabilities or any other concepts that are well studied from a different perspective. And it's not obvious other machine learning approaches are so prospective. It's still, as every approach, it's still a matter of research how to connect two different approaches in terms of making actual insight in the physics, on the physics part. So these operators have been, dynamical operators have been known in the field of dynamical system type of research that my collaborator worked with already almost a century, and they are there is a huge machinery in terms of applied math to describe them. However, just recently they gain a lot of attention because people are exploring how to approximate these operators from the data sets. And the way we do it is we actually apply machine learning tool that is actually, these are kernel operators, and we approximate dynamical operators through such kernels. And in principle, what we do, we build a kernel operator. Sorry, yes. In a delayed embedded space, so we built a distance that captures a short sequence of spatial patterns in some type of L2 norm. And afterwards, we put a kernel on that. So that's the nonlinear functions of the data sets. So that's already an attractive feature and improvement over linear type of operators. And there are a few other attractive aspects of that type of approach. Namely, one can approximate it and from the data sets, this type of operators, without any knowledge of the dynamics that is and equations that are at the underlying and driving the systems. Also, the derived patterns that we get it are invariant under any type of nonlinear transformation of the input data sets. And also, the derived eigenfunctions are having a high degrees of smoothness, and the eigenvalues can be associated with some type of measure of smoothness on the manifold, which is Dirichlet energy. So in principle, this method does not optimize for variance, which is quite important because some applications we work with we try to chase patterns that are not variance dominating, yet they are very dynamically relevant. So this there is a theoretical aspect that we really focus and we target temporal coherence of the pattern. So that's a very important improvement. And also, the other aspects is that we do these delay embeddings for a few different reasons. First of all, there are theoretical findings from 1980s by 8 attackers, but this type of procedures allows one to access degrees of freedom that otherwise one may lose by just using partial observations. And on top of that, we build a matrix. The kernel that I'm showing here is used to build Laplace-Bertrami operator after some type of normalization that is very well studied and attractive feature to build a database for nonlinear manifolds. And the other important aspect is that there is a lot of research on type of kernels one can work with. This is just a very simple ones. The other ones can adjust for density of the sampling. That's the ones we are experimenting with, and so on and so forth. But the most important part is that this approach allows one to show that the data-driven approximation with this type of kernels is actually approximate well these Koopman operators in the limit of long embedding windows. This is something that not every type of approach that is being proposed for Koopman operators can show and prove. So because of that, since these two Koopman operators can commute, they share eigenspaces and share eigenfunctions. And the eigenfunctions themselves are known for Koopman operators to be quasi-periodic and patterns that capture intrinsic timescales. And each one of them captures different type of timescales. And another important benefit of the approach is that it is really a good approach to study interactions across scales, different temporal scales. It's not really focusing on a given type of timescales, and there is no prefiltering needed to capture scales that are otherwise hard to access to. And and it's also very resilient to the noise. And here I'm just showing scalar value decomposition and how it and the results of this type of analysis when applied to the system I shown earlier, and the results on the right side. So one can see already an improvement in terms of capturing slow and fast timescales correctly without mixing them. However, there's still a problem with spatial part and interns and not capturing spatial correlations correctly. So the new approach that we work with is a vector value spectral analysis that is actually that is actually taking into account the same framework. However, it assumes that data sets that we work with is well characterized by vector value observations map. So for each data, each point in the data in a dynamical following dynamical evolution, one can associate spatial pattern vector that is obtained through vector value functions in some type of Hilbert space, and hoping that type of framework, one hopes to get access into spatio-temporal patterns that are actually quite tricky and ubiquitous in turbulence. So there are a few different complex assumptions I don't have time to go with, but but here is just a simple cartoon and comparison how scalar and vector value type of operators differ and how they also compare. So so in case of vector value operators, one does eigen decomposition of operator value kernels. So and the point is to choose it very smartly, and the way one can approximate it from the dataset. And here is the kernel. There's a lot of research how to do it correctly, given the fact we don't have access to the underlying phase space. And the way we approximate it with scalar value functions on the product space of temporal what is product space of space and time. And this is the product space omega is also allowing us access to the data to the observations, and we build a distance type of matrix in this type of space. And also we take advantage of the fact that two different scalar value functions on the product space is isomorphic to the vector value operators. So that's the way we can deal with the fact we don't have access to the phase space. And here is also very simple algorithmic comparison. So in case of scalar value kernels, we get a kernel that allows us to get temporal patterns, and this is of a dimension. The metric itself is of a dimension that is of a number of samples. In terms of operator value kernels, we'll deal with much larger matrix, and the output is actually spatio-temporal patterns. So we don't really have to, at this point, deal with spatio-temporal separability, and also we can show we do well with dynamical symmetries, and as well we are approximating Koopman operators and capture different timescales. And just to show the comparison, that's the result on the left, what's the potential when dealing with one of application. And the more complex applications that Björk hopefully will cover are related to Rayleigh-Bernard convection. So, and there's also a lot of potential in terms of capturing different timescales and so on.
Time for a few brief questions.
So you mentioned scalar, vector, and operator.
Yes.
I didn't quite get the definition of what the vector was here.
Scalar value operator here. I mean, scalar value operator is like in the sense the kernel is taking two different states of a dynamical system and is approximating it through bivariate functions that produce a scalar. So you get a you have a temporal, you have a spatial domain that is of high dimension spatially. However, you just compare it and assign with that just a scalar and just a number. In terms of vector value operators, you don't assume that. In terms of vector value operators, you take two different states of a dynamical system and you assign to that a linear operator. So which is actually, so it's a spatial pattern. It's that is obtained through vector value function that is acting on this spatial domain that is of your interest. So.
Any other questions? Do we have questions from outside?
Okay. Thank you.
Thank you. Let's thank you.